Your phone battery lasted all day when you first bought it. Now it barely makes it to lunch. This isn't planned obsolescence or bad luck. It's chemistry, and every single charge cycle is quietly killing your battery. By the end of this video, you'll understand the exact mechanism destroying your battery right now, and why some habits accelerate this process 10 times faster than others. Before we continue, drop a comment with your name and which city you're watching from. We love knowing where our audience is tuning in. Inside your phone is a lithium-ion battery. When you charge it, lithium ions move from the positive electrode, called the cathode, to the negative electrode, the anode. When you use your phone, those ions flow back. Simple, right? Here's the problem. Every time ions make that journey, tiny pieces of the electrode materials break off. Think of it like shuffling a deck of cards 10,000 times. The edges fray. The surface wears down. In a battery, this creates something called the solid electrolyte interface, or SEI layer. This layer forms on the anode surface. It's made of lithium compounds that can no longer move between electrodes. They're stuck permanently. Every charge cycle makes this layer thicker. A thicker SEI layer means fewer lithium ions available to store energy. Fewer ions equals less capacity. That's why your battery percentage drops faster after a year. The SEI layer doesn't form evenly. It grows thicker at points where the anode surface has microscopic cracks or impurities. These spots become hot spots for further degradation. As the layer gets thicker, electrical resistance increases. Higher resistance means the battery has to work harder to deliver the same current. This creates more heat, which accelerates SEI growth even further. It's a feedback loop. Within 2 years, some parts of your anode can have SEI layers 5 times thicker than others. This uneven degradation is why old batteries sometimes show wild percentage jumps, going from 30% to 15% in minutes. The battery management system struggles to estimate capacity accurately when different regions age at different rates. But capacity loss is only half the story. The other half is heat. Lithium-ion batteries generate heat during charging and discharging. This heat speeds up every degradation process we just talked about. At 25 degrees Celsius, your battery degrades at a baseline rate. At 40 degrees, that rate doubles. At 60 degrees, it quadruples. Your phone gets hot in 3 situations: fast charging, intensive apps like games or video recording, and leaving it in direct sunlight. Each time the battery hits 40 degrees or higher, you're aging it weeks in just hours. Here's where it gets counterintuitive. Keeping your battery at 100% charge is worse for longevity than letting it drain to 0. At full charge, the cathode is under maximum voltage stress. This stress causes lithium plating, where ions deposit as metallic lithium on the anode instead of inserting into it properly. Metallic lithium is reactive. It consumes electrolyte, thickens the SEI layer faster, and in extreme cases creates internal short circuits. The ideal charge range for longevity is between 20 and 80%. Staying in this range reduces voltage stress by half compared to charging to 100. Some manufacturers now offer optimized charging modes that learn your routine and delay the final 20% of charging until right before you wake up. This keeps the battery in the safe zone longer. The voltage curve of a lithium-ion cell explains why this range matters. At 20% charge, the cell sits around 3.5 volts. At 80%, it's near 4.0 volts. At 100%, it peaks at 4.2 to 4.35 volts, depending on chemistry. That extra 0.2 volts from 80 to 100% creates disproportionate stress. The cathode material, usually lithium cobalt oxide or a nickel-manganese blend, becomes unstable at high voltage. Oxygen atoms start breaking free from the crystal structure. These oxygen atoms react with the electrolyte, forming gas and degradation byproducts. You're trading 20% of daily capacity for months of battery lifespan. Now let's talk about the 0% myth. You've probably heard you should fully drain your battery occasionally to calibrate it. This was true for nickel-cadmium batteries from the 1990s. For lithium-ion, it's the opposite. Deep discharges below 20% cause voltage sag, where the battery struggles to maintain output. This forces the battery management system to work harder, generating more heat and stress. If you regularly drain to zero, you're cutting your battery lifespan by up to 30%. Charge whenever convenient, and keep it above 20 when possible. What about leaving your phone plugged in overnight? Modern phones have trickle charge protection. Once the battery hits 100, the charger stops pushing current. The phone runs directly from the wall adapter. But here's the catch. The battery still sits at 100% voltage all night. That's 8 hours of maximum stress on the cathode. Over months, this creates measurable capacity loss. The solution is either optimize charging features or just unplugging once you hit 90%. Fast charging deserves special attention. A standard charger delivers 5 watts. Fast chargers go up to 65 watts or more. That's 13 times more energy flowing into the battery per second. This energy creates heat. To manage it, phone manufacturers split the charging curve into 2 phases. From 0 to 50%, the charger runs at full speed. From 50 to 100, it slows down dramatically. This is why the first half charges in 20 minutes, but the second half takes another 40. The battery can handle high current when voltage is low. As voltage rises, the risk of lithium plating increases, so the system throttles back. If you want to preserve battery health, avoid fast charging unless you're in a rush. A slow overnight charge at 10 watts generates a fraction of the heat and stress. There's one more factor most people ignore: storage charge level. If you're not using a device for weeks, storing it at full charge kills the battery faster than daily use. At 100% charge, self-discharge reactions accelerate. The cathode material slowly decomposes even with zero load. Storing at 40 to 50% minimizes this reaction. This is why new phones ship with a partial charge, not full. If you have an old phone you're keeping as a backup, charge it to 50, turn it off, and check it every 3 months. Now let's address wireless charging. Wireless chargers transfer energy through electromagnetic induction. This process is less efficient than wired charging, typically 70 to 80% efficient. The lost energy becomes heat. That heat radiates into the back of your phone, warming the battery. If your wireless charger doesn't have active cooling, it can push battery temperature 5 to 10 degrees higher than wired charging. Over time, this adds up. Wireless charging is convenient, but if longevity is your priority, wired charging is better. What about battery management chips? Every phone has a dedicated chip monitoring voltage, current, and temperature across the battery. This chip makes thousands of micro decisions per charge cycle. It balances cells if your battery has multiple packs. It cuts power if temperature exceeds safe limits. It estimates remaining capacity based on voltage curves. These chips have gotten smarter. They now predict your usage patterns and adjust charging speed dynamically. But they can't overcome physics. If you consistently fast charge to 100 in a hot environment, no management system can fully protect the battery. Here's a practical decision you can make today. Check your phone settings for battery health features. Many Android phones and iPhones now show maximum capacity as a percentage of original. If you're below 80%, the battery has lost significant capacity. At this point, charging habits matter even more. A degraded battery has higher internal resistance, which means more heat per charge. Use slower chargers, avoid draining below 30, and keep the phone cool. One last thing, cold isn't better than heat. Below 10 degrees Celsius, lithium-ion batteries lose temporary capacity because ions move slower through the electrolyte. This is reversible, but charging a cold battery below 5 degrees causes permanent lithium plating. The ions can't insert into the anode properly at low temperatures, so they deposit on the surface instead. If your phone is cold, let it warm to room temperature before plugging in. This is critical in winter or if you keep your phone in a car overnight. Every battery dies eventually. Lithium-ion chemistry has a hard limit of about 500 to 1,000 full charge cycles before capacity drops below 80%. But how you reach that limit determines whether your battery lasts 2 years or 5. Keep it cool, avoid the extremes of 0 and 100%, and slow charge when possible. If you want to see more deep dives on the engineering behind everyday devices, subscribe to the channel. And drop another comment telling us where you're watching from. We read every single one.